Okay, reasons for popularity of control charts in the field of quality control. Okay, why these are extensively used in industries. These are the reasons. Quality control charts are a proven technique for improving productivity. Okay, if you make use of control charts, you can reduce the number of defectives. If you are able to reduce the number of defectives, obviously that will result in improving productivity. For example, if you are producing 100 units of a product, okay, out of 100 units, if there are 10 defectives, even though you have manufactured 100 units of a product, now only 90 can be released into market because remaining 10 are defective. Okay, instead of that, if you are able to reduce the number of defectives from 10 to 5, again if you produce the same 100 units of a product, now you are able to sell 95 units of a product in the market because you have reduced the number of defectives from 10 to 5. Okay, so that's how we can improve productivity using control charts. It is with the help of reducing number of defectives by keeping the process in control. These are effective in defect prevention. So that also we discussed in previous class. Okay, so how we can take out of control, how we can prepare out of control action plan. Okay, which can be used to prevent defect. Okay, and also identify and prevent the cause for prevent the reasons for assignable causes. Control charts prevent unnecessary process adjustment. Okay, since it is a continuous improvement tool, okay, continuously are focusing on reducing deviations in the process. Okay, you can find process parameters, optimal process parameters with the help of these control charts. Okay, continuously you can upgrade and you can improve and you can avoid unnecessary process adjustment since you are familiar with the optimal process parameters. Okay, you can operate the machine with those optimal process parameters. Next, control charts provide diagnostic information. Okay, in previous class we discussed. Okay, so we can have an action plan where we can list the assignable cause and how it can be removed. Okay, so or how it can be addressed. That list we can do. So that is the diagnostic information. If the same type of problem or assignable cause arises, okay, you have the set of procedure which need to be followed to avoid that or to remove that or to eliminate that assignable cause. Okay, so that is the diagnostic information. Next, control charts provide information about process capability. Okay, so already we discussed about process capability in detail. Okay, control charts also provide information about process capability. Okay, so if the process is in control, okay, so obviously process capability will be good. If the process is out of control, then process capability will be less. Next, choice of control limits. Okay, in previous session we discussed about the structure of control chart. It consists of center line, that is nothing but mean, okay, mean of the population, and there are limits, upper control limit and lower control limit. So this is an example where they have considered flow width, like we considered an example of hard bake process in previous session where we are considering the quality characteristic as flow width. Okay, same example. So they fixed upper control limit as 1.7013 and lower control limit as 1.2987 by using the equations for upper control limit and lower control limit, that is mu plus L sigma and for lower control limit mu minus L sigma. Okay, so where L is the standard deviation units, okay, and sigma is the standard deviation value. Okay, that we will understand later. Okay, but now in order to plot control chart, so what are the things we need is, so first we should decide what is the quality characteristic. Like in this example, it is a flow width. In some cases, it may be a dimension, okay, dimension of the physical product or any other quality parameter. Okay, sample number. if you are considering, if you are picking 20 samples from a lot of 1000 units of a product, okay, so then you have to number them, sample 1, sample 2, sample 3, like that. That is the sample number. Okay. Next, how to choose these control limits, okay, where they should be kept. For that, there are many considerations. Specifying the control limits, that is this upper control limit and lower control limit, is one of the critical decisions that must be made in designing a control chart, because we are evaluating whether the process is in control or out of control based on the location of the points. Okay, if the points lie beyond this upper control limit and lower control limit, so we evaluate in detail, okay, whether the process is in control or not. Okay, what is the reason for getting points out of these control limits. Okay, like that we are going to evaluate. In order to do that, first we have to fix what is the upper control limit and what is the lower control limit. So that's why it is very important to specify the control limits, and randomly you cannot fix these values. Okay, there must be some basis. You must have understanding of the process which you are performing or which you are evaluating. Okay, what is the deviation, how much deviation you can expect. Okay, what is the acceptable level of deviation, okay, or variation. All these things you should know. Based on that, you can fix this upper control limit and lower control limit. So suppose if you go for widening these control limits, there is a problem. If you go for reducing the width of these control limits, again there will be one more problem. Okay, so this must be optimal. It should not be wider and it should not be narrow. Okay, so like that you have to choose control limits. By moving the control limits farther from the center line. Farther means if you make these control limits wider, okay, instead of taking it at 1.7, if you move on to 1.8, and instead of taking at 1.3, if you fix the lower control limit to 1.2, then so we are able to gain one advantage, that is we can decrease the risk of type 1 error, that is concluding the process is out of control when it is really in control. So that means, so if you fix this upper control limit and lower control limit nearer to center line, okay, there is more possibility that you may get few points out of this if the control limits are narrow. Okay, but the process may be in control because you are fixing these control limits to a nearer value nearer to central line, so you are getting some points, okay, beyond that, but actually the process may be in control. Okay, so by moving the control limits farther from center line, we decrease the risk of type 1 error. So you can, in order to reduce that type of risk, okay, you can go for broadening or the widening the control limits, but again there is a disadvantage. Okay, so we decrease the risk of a type 1 error, concluding the process is out of control when it is really in control. Okay, so next, however, widening the control limits will also increase the risk of type 2 error, as we discussed. If we go for widening the control limit, so that may end up in concluding the process is in control when it is really out of control, since instead of fixing upper control limit and lower control limit at these values, okay, if you go for 1.8 and 1.2, you may not be getting any of the values out of these control limits, but that doesn't mean the process is in control, because unnecessarily you have widened the control limits. Because of that reason, even though process is in out of control, you are getting the points inside the control limits. Okay, so these are the things which will happen. Okay, so it should not be narrow and it should not be too much wider. Okay, so both have their own advantages and disadvantages. Next, two limits on control charts. Okay, there are few quality experts, okay, who suggest to have two limits on control charts rather than having only one limit. One limit means it is only about upper control limit and lower control limit. So this is one set of limits. Having two sets of limits means other than control limits, so have warning limit. Okay, upper warning limit and lower warning limit. So if you have these warning limits, okay, so there are advantages, there are disadvantages. Okay, for example, so in this case, Okay, so upper control limit and lower control limit are fixed at 3 sigma. That means by considering 3 deviation values, okay, 3 standard deviation values. So here in this example, they are fixed at the control limits. Okay, so include warning limits, it will be kept at 2 sigma. So like in this example, okay, warning limits, upper warning limit and lower warning limit. Okay, so these are calculated like this. So again, same formula using this formula, upper control limit. So I have this. Okay, so here instead of, if you take it as 3 sigma, okay, substitute 3, you will get this value. Again, here if you substitute 3, you will get this value. Okay, so in order to find out warning limits, so instead of 3, you are considering 2 sigma, okay, plus or minus 2 sigma you are considering. Okay, the use of this warning limit is, suppose if some points, okay, go beyond this warning limit, but if they are within the control limit like this. Okay, for example, so you may be having some point here, and also you may be having a point here. Okay, so if you have a point here, so no doubt that it is if there is a point, okay, at this location, okay, no doubt that so it is out of the control limits, okay, and we will evaluate in detail. So there are cases where so few points may not be out of the control limits. Okay, so these, if you consider these 3 points, this and this, okay, these 3 points are within the upper control limit and lower control limit. Then also, since they are at the border, okay, border of these control limits, there may be a possibility that so this may be also giving a signal about presence of some of the assignable causes. Okay, so if points lie beyond these warning limits, okay, so one who is looking at the control chart has to pay attention. Okay, even though if they are, these points are within the control limits, since they are beyond these warning limits, so some attention need to be paid by the one who is looking at control chart for quality control. Okay, so for evaluating whether the process is in control or out of control, so he has to look at these points. Okay, so that is the warning limit. So this is like taking precaution. Okay, so and paying attention. Okay, so even though points may be within the control limits, then also so engineers are taking precautions. Okay, so if they make use of warning limits. Okay. The outer limits at 3 sigma are the usual action limits. Okay, this upper control limit and lower control limit are action limits. The inner limits usually at 2 sigma, like these two. Okay, upper warning limit, lower warning limit are called warning limits. The upper and lower warning limits are located at 2 sigma. So that is, we are substituting L value as 2. Of warning limits can increase the sensitivity of the control chart, since even though these points are not out of the control limits, then also you are evaluating these points in detail. Okay, whether these are manufactured when the process is in control or out of control, why you are getting the points almost nearer to the border of this upper and lower control limits, what is the reason, like that you are evaluating. That means you are increasing the sensitivity. That means you are evaluating in detail, even though points are within the control limits, so you are evaluating. That will increase the sensitivity of the control chart. Warning limits allow the control chart to signal a shift in the process more quickly. Since you are finding it before the points are going out, okay, so you are taking precautions early. Okay, so you are able to prevent something which may occur in future. One of the disadvantages is that they may be confusing to operating personnel, because since there are 2 limits, both above and below, so 2. Okay, it may be confusing for a person who is looking at the control chart in order to ensure that he is not going to get points out of that are in order to ensure that process will operate in control. Okay, so this may lead to confusion. Next, sample size. Okay, so it is very important in inspection. Okay, whenever you are inspecting, okay, so you have to um, say make a decision regarding sample size. Okay. Suppose if you are manufacturing 100 units of a product, okay, uh, evaluating for inspection, choosing 10 or 20. Okay, if you have two options, so you are working as a quality engineer in a company and you are producing 100 units in batches. Okay, in every batch you are producing 100 units of a component. Okay, after producing this 100 units of a component, now you have to choose some units. You have to pick some samples. Okay. Now, is it better to take 10 units or 20 units? Which is better? Out of 100 for inspection, taking 10 or 20, which one is better? Okay, you have to answer. Anyone can answer. Okay, out of 100 for inspection, sample size. Okay, choosing 10 or 20, which one is better? 20 or 10? Charan Raj, Charan Raj MR. Chinmay MG, Chinmay, Gagan Bildi. Okay, if you don't respond, I assume that so you are logged in and now you are not listening to class. Okay. So again, so out of 100, if you choose 20, it is better. Okay, since you are evaluating more number of units, it is better. Okay, that is positive side of choosing a higher value of sample size. But there are demerits. Okay, it will consume lot of time, lot of effort. Okay, so that is a disadvantage. So now you should choose a sample size such that it is not more and it is not less. Again, it should be a optimal number. Okay, larger samples will make it easier to detect small shifts in the process. Okay, suppose if your intention is to identify small deviations, small variations, then you should go for larger samples like out of 120, that is the larger sample. You can go for this larger sample when you want to find small deviations. Okay, small deviations from the target, that is known as small shifts. When choosing the sample size, we must keep in mind the size of the shift that we are trying to detect. Okay, if you want to find out large shift, that means large deviation, then we can go for small size. Okay, suppose if you are manufacturing a component, cylindrical component having 18 mm diameter. Okay, like this section. Okay, this is a cylindrical section having 18 mm diameter, for example. Okay, suppose if you want to find a deviation of 0.05, then you should go for larger samples. If you want to find a deviation of 0.5 mm, okay, so then you can go for smaller sample size. Okay, because deviation you are considering is 0.5, which is large compared to 0.05. You can go for small sample size. Okay, so like that there are considerations. If the process shift is relatively large, then we use smaller sample sizes. it is desirable to take small samples at short intervals or large samples at longer intervals. Okay, another important concept is so sampling frequency. Okay, how often do you take these samples? Suppose if a manufacturing company is operating for an 8-hour shift, if the machines are continuously working for 8 hours, if they are in working condition for 8 hours, okay, when will you take the samples? Whether at the beginning of the shift or at the end of the shift or after 1 hour, or what is the criteria? Okay, so that is the frequency. Okay, how often you will take these samples? Next, sampling frequency, that is how often we will take samples. The most desirable situation from the point of view of detecting shifts would be to take large samples very frequently. That means if you take samples, suppose if the company is operating for 8 hours, if you take samples for every 30 minutes, it is good than taking samples for every 1 hour. Okay, but again there are problems. Okay, resource time consumption, it will be more. But if you take samples frequently, that is better in the point of view of ensuring quality, ensuring process control. Okay. The most desirable situation from the point of view of detecting shifts would be to take large samples very frequently. And again, if you are able to take large samples very frequently, that is preferable. But always there is a problem of economic feasibility. That means you have to invest more money on people who need to do inspection. Okay, so it will take time, money. Okay, desirable to take small samples at short intervals or larger samples at longer intervals. Okay, in order to trade off between okay economic feasibility and quality. Okay, so you can go for these things. Okay, if you are taking small samples, okay, out of 100, if you are only picking one unit for inspection, okay, that is a small sample, then you can go for short intervals. That means instead of evaluating 4 out of 100 units after 1 hour, okay, you can go for evaluating 1 unit after every 15 minutes of production. Okay, that is small samples at short intervals. Larger samples at longer intervals means you can, there's another strategy, you can go for evaluating 4 units, 4 out of 100 after 1 hour, or 8 out of 100 after 2 hours. Okay, so like that we can so go for choosing this sampling frequency. Current industry practice tends to favor smaller, more frequent samples. That means if this sampling frequency, the time between taking two samples, if it is more, okay, so the problem is, so you may be end up with producing more number of defects since you have not taken sample for evaluation for a longer period. Okay, during that period you may end up with production of defective products. In order to avoid that, so in industries, so they always they prefer to go for smaller samples, but with more frequently they will do pick them. Okay, particularly in high volume manufacturing process. That means in mass manufacturing, mass production, okay, or where many types of assignable causes can occur. Suppose if you are expecting deviations because of many reasons, because of error from operator, because of problems in the raw material, because of machine. Okay, if there is a possibility of getting defectives, okay, then you should go for again smaller and frequent sampling, small sample size and more frequent sampling. Okay, now because of the technologies, okay, now it is possible to do inspection without human assistance. Okay, we can automate the process of inspection. Okay, so because of that reason, now we need not depend on manual labor. Okay, we can fix a sensor, okay, which can measure a particular parameter, and same data can be stored in a computer system. Okay, and that can be converted into a control chart, and that can be analyzed by the software itself, or a person sitting in front of a computer. Okay, he can evaluate. So this is possible with the help of automation technologies. Okay, now you can go for taking large number of samples, because it will be done automatically. Okay, it will not interrupt the production. Okay, so online inspection is possible because you are using sensors for measurement. Okay, and again you are using statistical process control softwares for getting real-time data. Okay, based on all these things, it is possible to take more number of samples, or even you can evaluate quality of each and every product with the help of automated inspection technologies. Okay, by automating the process of inspection, it is possible to evaluate each and every product. Okay, as automatic sensing and measurement technology develops, it is becoming possible to greatly increase sampling frequencies. Ultimately, every unit can be tested as it is manufactured, because it is not done manually. So if you fix a machine at a particular location, it will measure a particular quality parameter, whatever components which are passing in front of it. Okay, so that is possible. Automatic measurement systems, and even by with the help of machine vision. Okay, so you can do this. Automatic measurement systems and microcomputers with statistical process control software applied at the work center for real-time online process control is an effective way to apply statistical process control. Okay, because of this automation, the whole discussion towards picking samples, okay, and deciding on sampling frequency has changed, because it is not done manually. Okay, since it is because of a technology, because of sensors, okay, because of data capturing technologies. Okay, all this can be done in a different way. Okay, with very less resources, and again we may be able to get better quality also. Another way to evaluate the decisions regarding sample size and sampling frequency is through the average run length of the control chart. Okay, it is like after how many samples. Okay, so or after how many units of evaluation, okay, a point may lie outside the control chart. If you plot 20 samples, okay, suppose after on an average after 10 samples, if you are getting a point outside the control limit, that means average run length will be 10. Suppose, okay, for example, you can apply this average run length for online classes also. Suppose if you lose interest for listening to lectures after 10 minutes, okay, that means we can expect that after 10 minutes, so you will not listen to lecture. That is the average run time. Okay, so a 10 minutes duration is the average run time. So like that, how frequently a point will lie out of the control limit. Okay, so that is the average run length. Average run length is the average number of points that must be plotted before a point indicates an out of control condition. Okay, suppose if you plot 10, okay, if 9 will be within the control limits and 10th one will be out of control limit, so then the average run length will be 10, okay, or 9. So if 9 are inside the control limits and 10th will be outside, then 9 is the average run length. Okay, after 18th, so another will run out. Okay, so like that it is an average. So if the process observations are uncorrelated, so in previous session we discussed the meaning of correlated, auto-correlated, okay, so all and stationary, all these things we discussed in previous session. If the process observations are uncorrelated, then for any Shewhart control chart, the average run length can be calculated easily from this equation. Average run length, that is given by 1 by P, where P is the probability that any point exceeds the control limit. So what is the probability? Based on that we can find out average run length. That means after how many points, so you will get a point which is out of the control limits. For the chart with 3 sigma limits, so the value of this P will be 0.0027. Okay, how we are going to get this? Based on this. Okay, so here you can see percent inside specification limits. Okay, if you choose plus or minus 3 sigma, that is these two values. Okay, 99.73% of the points will lie within plus or minus 3 sigma. Leftover will be only 0.27%. Okay, this is for 100%. Now, if you apply the same thing for 1 unit, okay, you should divide this 0.27 by 100. So that will give you 0.0027. Okay, so like that you will get this value of P for 3 sigma limits, because 0.27% points will lie out of plus or minus 3 sigma. And since you are considering this P value for a unit, okay, for a single point, it will be 0.27 divided by 100 and you will get this value. P is equal to 0.0027. Okay, for the control chart with 3 sigma limits, P is equal to 0.0027 is the probability that a single point falls outside the limits when the process is in control. Therefore, the average run length of the control chart when the process is in control is, for this example, if the P value is 0.0027, 370. Okay, that means, that is, even if the process remains in control, an out of control signal, that is, a point may lie out of the control limits, out of control signal will be generated every 370 samples on an average. This is an average. It may not be after 370 and after 740, it is not like that. Okay, in between that it will happen, and an average for every 370 samples. So you can find 1 point out of control limits. Okay, so one signal you will get for 370 samples. This is another way to decide on sample size and sampling frequency. Now you will get an idea. Yeah, sampling frequency should be for after 370 samples. Okay, what is the time that will be taken to produce these 370 samples? Based on that, you can decide on sampling frequency. Okay, then suppose if there are if you are manufacturing 1000 units. Okay, if the ARL is 370, okay, you can go for sampling size as 3, okay, or you can go for 5. So based on this, okay, you will get an idea, okay, for how many samples you will get a signal regarding out of control, or how many samples you will get a defective. So the meaning of this is, for 370 samples, you may end up with 1 sample or 1 unit which is defective. It is also occasionally convenient to express the performance of the control chart in terms of average time to signal. So there we consider number of samples. Here we consider that in terms of number of hours. If samples are taken at fixed intervals of time that are h hours apart, then so multiply ARL with h, so you will get average time to signal. Okay, so indicates that there will be a false alarm about every 370 hours on an average. Okay, next, rational subgroups. Okay, while sampling, you can group the units manufactured. Okay, suppose if a manufacturing company is producing 1000 units per shift, okay, for 8 hours. For example, suppose instead of 1000, for 8 hours, if a 8-hour shift, if a manufacturing company is producing 800 units of a product. Okay, next, is it possible to group them? Okay, suppose if out of 800, if you are choosing 80 samples for quality inspection, again out of these 80 samples, if it is possible to identify the reason, okay, for defects, you can consider them and you can group them. okay, based on different approaches. Okay, so we will understand it in a better way by discussing few aspects. Okay. The rational subgroup concept means that subgroups or samples should be selected so that if assignable causes are present, the chance for differences between subgroups will be maximized, while the chance for differences due to these assignable causes within a subgroup will be minimized. This is like choose grouping samples, okay, like formation of a homogeneous group where all members are alike, okay, they have similar things, okay, or they are similar mindset. Okay, so the qualities of the samples are same within a group. Okay, when you are comparing a sample in one subgroup with another subgroup, you can find lot of differences. But the difference within the group, within the subgroup, should be minimum. Like that, you have to form subgroups. Okay, time order is frequently a good basis for forming subgroups because it allows us to detect assignable causes that occur over time. So this is one strategy adopted to form subgroups where you are grouping products. Okay, suppose if it is say 8-hour shift. Okay, you are grouping. If you are taking 5 samples. Okay, you are taking 5 samples after 1 hour. You are taking another 5 samples after second hour, again 5 samples after third hour, okay, again after 4, 5, 6, 7, 8. Because so how is it better to make subgroups like this means? So at the beginning of the shift, okay, there is a possibility that worker may have interest to operate machine since it is the beginning of the shift. Okay, he will be okay, so he doesn't have the fatigue. Okay, because of that he can concentrate on machine, he can operate the machine properly. Even machine at the beginning it can perform well, okay, after few hours. So even worker may lose interest because of work fatigue, and even machine may show some deviations, okay, because it is operating for many hours. Okay. Okay, so this we'll understand with the help of the graph. Okay, so this is a graph. Okay, so with the help of this we will understand. Before that, we'll discuss about two approaches. Okay, so there are two approaches to construct rational groups. One is snapshot approach. Another will be random sample approach. In snapshot approach, as we discussed, we will consider time. Okay, after 1 hour, after 2 hours, after 3, 4, 5. Okay, after 1 hour, we will pick 5 samples. Okay, after 2 hours, so we will pick 5 samples. After 3, we will pick 5. So here time will decide. Okay, based on time, the concentration of human operator will also vary. The machine performance are also vary with time. Okay, by considering this, we can go for snapshot approach. Each sample consists of units that were produced at the same time or almost nearer, okay, at the same time or as closely together as possible. Okay, immediately. Okay, whatever produced after 1 hour, 1 hour 30 seconds, 1 hour 60 seconds, okay, 1 hour 1.5 minutes, 1 hour 2 minutes, like that immediately you are taking samples. Okay, because of that the quality of the samples may be almost same. If there are deviations also, they are very minor deviations. Okay, so this approach is used when the primary purpose of the control chart is to detect process shifts. So here what you can get is, so when process has shifted, whether it has shifted after 1 hour, after 2 hours, after 3 hours, after 4 hours, when the process shift, okay, that you can analyze with the help of this snapshot approach. Next, there's one more approach, the random sample approach. So randomly you will take sample. Okay, it may be after 30 minutes, then it may be after 2 hours. Okay, it may be after 2 hours 20 minutes, then it may be after 2 hours 30 minutes. So here you don't have a fixed time interval between taking samples. You will pick whenever you want. Okay, but there is one more condition. Whatever samples you are picking, okay, that sample should represent the remaining units, okay, so of that interval. Okay, so that is the consideration. Okay, so here in random sample approach, each sample consists of units of product that are representative of all units that have been produced since the last sample was taken. Okay, for example, so if you are producing 800 units, okay, and if you are taking 80 samples, okay, so after producing 50 units, if you have chosen one unit, that means one component as a sample, that one component should represent remaining 50 which were manufactured from the beginning. Okay, it should have those deviations in remaining 50. If there are errors in remaining 50, deviations in remaining 50 units, that should be also reflected on the sample. Okay, so like that sample should be taken. This approach is used when the control chart is employed to make decisions about the acceptance of all units of product that have been produced since the last sample. Okay, if you are able to pick a sample like this, okay, 1 out of 50, where this 1 is representing all 50 in all aspects, like its quality in terms of deviations, okay, the level of deviation. And if you evaluate only one, you should get a picture regarding all 50. Okay, so this will be used when you can make a decision regarding what is the quality of all 50 by considering this one sample. Okay, so this is the representation of snapshot approach. So here time, okay, after if it is in hours, okay, so time after 1 hour, so you are taking 5 samples immediately one after other. Okay, 5 samples you are taking at a time. 5, 6, 7, 8, 9, 10th hour, 11th hour. Whereas in case of a random sample approach, so randomly you are taking samples. See, 0 to 1 hour. So within that you are taking almost 4 samples. Okay, then between 1 to 2, so you are taking samples here. Okay. So this is the random sample approach. So here you are considering a fixed time interval of 1 hour to take 5 samples. So here randomly you are taking samples. Okay. And if you and these values are indication of shift in mean, process mean. Okay. So earlier mean was here. Now mean shifted to this position. Again it come back to this. Okay, so there is, from this what you can understand is there is shift in process mean. Okay, next, so if you plot X bar chart and R chart for these values, okay, for these samples, the chart will look like this. Okay, this is the X bar chart and this is the R chart. Okay, X bar chart, so is the measure of central tendency. Okay, R chart is the measure of deviation or dispersion. Okay, so here by using this, you will get an idea regarding is there a shift in process or not. Okay, process shift. You will get an idea regarding process shift. If there is shift, what is the level of the shift? That idea you will get with the help of this chart. Okay. Next. Here also it is a chart. Okay, so used to based on these values. Okay, here you will get an idea regarding, okay, so how there is shift in process mean, and also you will get an idea regarding whether the points, whether to accept a particular sample or not, whether to accept or reject a particular unit of the product. That decision you can make with the help of this.